Otherwise, we can do this.
That's fine. Thanks. Okay, so hi, I'm Sahar. I'm a postdoc at the Weizmann Institute in Israel, working with Barak Zakai. And I'll tell you about separating orbital radial velocities for the spectral shape variations. Now, here's the problem. That's a simulation, courtesy of Finan Zhao and Xavier Dumusk. These are the radial velocities extracted from a simulated spotted sun-like star. And what we see here is that we have a signal induced by the stellar activity, it is in red, and some signal induced by a simulated planet in blue. And the goal of this talk would be to show a new inference method to derive the radial velocities induced by the planet in blue, while kind of mitigating the effect of the red ones. To do so, we need to factorize the spectra. I will tell now what I mean by that. So earlier today, Francesco told us about convolution kernels, right? Now, let's imagine that we have a perfectly quiet star. And by perfectly quiet, I mean that at each parcel on the surface of the star emits exactly the same emission pattern, no matter what. And we know how to model that pattern, let's call it F naught. If we want to integrate how an observer on Earth will look at it, we need to take each area element on the face of the star, shift it to the frame of the observer, and then integrate over everything. That's basically the convolution. And it looks like that. That is one of the standard practices. Now, on the left, you see an example. You see that is how a rotation convolution kernel would look like. And what we take the seed spectra, we convolve it, we get a template, and then we match the template to find the velocity. Okay. But what happens if our model or if our star is imperfect? For the sake of discussion, I will talk about temperature fluctuations. So let's assume that now the surface of the star is not as constant, and each parcel on the surface of the star emits according to a slightly different temperature, maybe a bit hotter, maybe a bit colder. And I will further assume that I could, even though each part emits slightly differently, I will imagine that I can present the emission per area element as some series of functions. These are the F naught and F1 and so on. Okay? What are these high order terms? So the first term is just the model for the quiet star. And the high order terms, if we talk about temperature fluctuations, would be simply the Taylor approximation for a given temperature. So you could see a map of interpolated Phoenix models. One axis is the temperature, another one is the wavelength. And the dotted horizontal line represents the 0th template. And the top panel shows how a regular template would look like. And these two are the first two derivatives with respect to the effective temperature. And what we see is that there are lines that respond very quickly to change of temperature, while other lines don't. Now, we can use it. We can use it to estimate what happens per parcel on the surface of the star. But to do it in practice, see if it works. Okay. We need again, now previously it was kind of easier because all we needed to do is one convolution kernel, but now we need to propagate all these high order terms down into how we present the spectra. So the process is exactly the same. We take the flux, we shift it to the frame of the observer, it's just a convolution with the delta function. We put in the linearized terms, we integrate over the surface area of the disk of the star, and eventually we're left only with a convolution kernel that depends on the wavelength. So basically what we get in the end, instead of one convolution kernel, we get a sum of several convolution kernels, one for the basic quiet star and other for the high order terms. And this is useful. Now let's see what each one of these does. The first term, U naught, the first principal kernel will hold the rotational broadening, the Doppler shift. and its corresponding flux will contain the spectrum of the quiet star. F1, which is the first high order term, will contain the first derivative with respect to the temperature, and its corresponding kernel will tell us where the spot is located and what's its size or contrast. Now, it sounds like a hard problem to take and infer the shapes of the kernels. It sounds okay, we have like many kernels, and how can we derive? Do we have enough data in a single spectrum to derive it? And we claim that there is enough. And let's see why. When we usually think about, when I usually think about kernels or spectra, I think about continuous functions, but this is not really the case. These are actually discretely sampled functions. And the sampling resolution is, say, somewhere between 100 or 1,000 meters per second. And we have, say, 50,000 to 500,000 samples per spectrum. Now, how many numbers do we need to derive, actually, to fit it? So each broadening kernel has this nice property. It drops to zero very fast. It cannot be non-zero everywhere. You cannot mix contributions from very distant places of the star. It would only be a few kilometers, 10 kilometers, whatever it is, but it will be on the order of 10 kilometers per second, or maybe less in some cases. And it means that per kernel, we need to constrain up to 10 or 100, depending on the sampling, parameters. Even if we have like, say, 10 kernels, we still have enough data to fit everything. And this establishes that inference is possible, even if we fit 10 kernels, several high order terms, but it doesn't tell us how to do that. And we need an algorithm that will allow us to take these kernels and fit for them. And we do it using short time Fourier transforms. Now, instead of talking about the wavelength domain, now we'll talk about the Fourier transform. So everything that was convolution before is now a very nice product of the Fourier transform of the kernel and the corresponding Fourier transform of the spectrum, or the part that we are fitting for. Now let's imagine that for the sake of discussion, I use a shell spectrum, okay? And I start by analyzing the red order. I write down the equations, and then I want to shift to the green order. Which part of the equation will change? So if the flux contribution is in the principal spectra in F0, F1, F2, the things that will change will be over there. The principal kernels will remain the same, even if I switch, even if I look at a different spectral order. And that's a nice property because it will enable us to fit it. Now, specifically, the first kernel will contain the Doppler shift. It will be just the complex phase of this kernel. How can we fit all the parameters? Let's go through the process. We take each order of the spectrum, we put it like that on top of its head, and we take its Fourier transform. And then we go to the next one and so on. So we take all orders of the spectrum, flip them, take their Fourier transform, okay? That if you would observe, if it was GW, we would look for chirps in that. That's a time frequency diagram, essentially, right? Now, the nice property in this factorization is that the parameters that we are trying to fit are shared for all segments in the spectrum. So when we try to fit for the kernels, all we need to do is to fit for these parameters, C0, C1, C2, which represent our kernels, per zeta. So we go one row at a time and just find these kernels. That's now an easy thing to solve. It's a least squares problem, and we can show that solving the least squares problem in this domain is mathematically equivalent to solving it here. It is just way easier. Now I'll show you some examples in the time that I have left. So let me try to convince you that we can actually fit. Here we injected a nice spot. You can see its effect over here. It's a 200 Kelvin contrast. Can we fit it using the approximated Taylor series-like model? And this is below the residuals after we fit. If you look at how the effect look like, it looks like the derivatives, actually. So it's easily fitted. But can we extract radial velocity? Yes, we can. Again, this is the model we fit from the first parameter. The complex, the phase of the first parameter contains the radial velocity information. And now what you look at is a Monte Carlo simulation. So we drew 10 spots, added it into the spectrum and fitted for it. Each spot was ascribed with a different contrast, different velocity. And the center of mass velocity of the simulated star was 75 centimeters per second. You see the histogram of the resulting velocities. So we get back 75 plus minus 25 centimeters per second. We can find it. If we would compare it to a standard CCF search, we've improved by a factor of 4 or 5. They scatter due to the noise. And this effect, we can now, to convince us that it works, we can actually look how it behaves as a function of the SNR of the simulated spectrum. And we drill down like shot noise, while CCF scatter will reach a limiting value, right? In this simulation, it's a meter per second, but it depends. So to summarize, I've introduced an inference method. The inference method is designed to find the radial velocities in the presence of weird things that happen to the spectrum. There is enough information to do it with a single epoch. And we can fit for that. And short time Fourier transforms gives us a way to do that. But we do need to have the high order terms. Here I assumed that everything comes from temperature variations. That's not always the case. And we need to have physically inspired high order terms. It could be, say, magnetic field. It could be the position on the surface of the star, or whatever parameters that we think of. We need to have these in order to be able to use this technique. We are working on an alternative to empirically derive this function. It has some promising results. And this is it. I think with this, I will take questions.
All right. Any questions for Shahar? Did we have any online in the Slack? Nothing at the moment. Oh, we do. Okay.
This is Eric Ford saying nice work. 2 questions. In practice, the spectrograph has a line spread function, LSF, that varies with position on the detector. In principle, the variations can be measured with calibration data, but those won't be perfect. So I worry that there might be a near degeneracy between the LSF and convolution with a stellar rotation. Have you looked into whether this is a significant concern?
So that's an excellent point. What we used is basically, we talked about temperature fluctuations, but everything that is chromatic and can be modeled can be treated as a high order term. So line spread function variations can be treated if we can model them correctly for a given instrument as high order terms, and we can fit for that as well. So I think this framework is actually suitable for that.
Excellent. Let's thank Shahar again and get our next speaker.